All right. I guess we get started. Right. Um. Good morning, or evening, or afternoon, everybody. My name is Ming. Uh, your I'm your classmate, but I'm also a biotechnology master student. So I was tasked with giving us a quick review of this paper, namely the paper on the identity inference of genomic data using long-range familial searches. I am not qualified to teach anything to anybody, but I find this paper is absolutely amazing and very, very interesting. So please let's take a look. It was written by Ehrlich and co-workers. I'm not sure I pronounced that right. Ehrlich, maybe. And it was published in Science in 2019 or 2018. Science is probably one of the two most important and high impact publisher in the world. So you know that this paper is legit. Anyway, so the roadmap today will be fairly simple. I will first try to introduce the terms and concepts that we need to understand this paper, and then we would go into the paper objectives. Then I'll talk about the methodology and the results that they got, and then we'll discuss a little bit on the implication and the author's opinion on the matter. So start with the terms and concept because I don't know about you guys, but for me it was a little bit confusing at first. So we are dealing with genealogy. Now, genealogy comes from the word genealogia from Greek. This means making a pedigree, and this is a study that focuses on family, family history, and lineage. It is not a new era of study. From the dawn of time, we always try to keep track of who is the son of whom, because that's how we keep track of people in our society. You can go all the way back to the Bible. They always refer to someone is a son of someone or like the daughter of someone else. So it's very, very old, it's old time. And traditionally, it requires actual knowledge of the family history. It's basically, if no one is around when that person give birth and no one can give witness to it, it's hard to say who is who. So that was the traditional meaning and application of genealogy. But there's a new era of genealogy, which is what the paper is focusing on. Uh, there's a new era because it has become independent from prior knowledge with genomic data. If the two people are basically this very, very similar in terms of their genomic contents, then um, it's safe to say that they're related, more so than someone else that have a lot less similarity between the genomes. This doesn't require any prior knowledge, like you don't have to be there when that person was born or know their family to know this for a fact. And we having an immense database. So estimated in 2020, at least 30 million people have done DNA tests globally. It's been 3 years since then, so this number could only increase. And we have unprecedented accuracy with our techniques now, because before, uh, if you guys watch Game of Thrones like I do, you know that sometimes the children of someone might not be actually their children because infidelity is a thing. But with DNA test, you cannot fake that because it is in your DNA. It's, you can't do anything about that. So how does it work? How does it work actually? So the paper is dealing with commercial utilization of DNA testing and familial searches. So how does it work from a simplified point of view? Now we have a few parties over here. We got the genotyping service provider, also known as the DTC. Here I put 23andMe, which is the largest company that in this field. As an example, we have the customer, which is us. We have the database or the analyzer that holds a large database of human genome so that we can compare it to. And on the other side of user, we have the police or authorities, which are not which are non-civilian user per se. Now, first, the DTC would sell the kit directly to the customer. We would buy it, and then we would send back the sample. In most cases, it's just saliva sample. You spit in it, and then you send it back. They would genotype it, and they send out the data to us. Obviously, we are not very well equipped to read that data, and more importantly, we don't have a database to compare it with, so we would have to send it down to the GED match, which is the biggest database analyzer on the commercial side. We upload the data over there. They and then they would analyze it, and they would send us back the information on our family history. I don't know why, but in 2019, 2018, there was a big trend of trying to find out if you were, say, 20% Irish, 18% Italian, 12% Turkish. That kind of trend was very, very popular, and that what exploded these databases. Because once you upload the data to GED Match, it gets retained. So say that 100 million people, sorry, 100,000 people use that data, the service, then 100,000 more data point would be collected to GD match. So the database gets bigger and bigger, and the bigger it gets, the better it becomes. For the police, it's actually a lot easier because they have their own lab. So they would just sequence the DNA from the sample from the crime scene, and then they would send it to the analyzer, and they would send it back a list of possible relatives to the suspect. That's the flow of information. But how does it actually work? How does the DTC, in this case 23andMe, sequence your data? Well, the thing is that they don't actually sequence it because 99.9% of humans share the same genomic contents. Very, very tiny differences in the genome or differences in our phenotypes. So instead of trying to sequence everything, they actually probes around 700,000 genomic variants. These are sites that are known to be different between one person to another, and by probing these sites, we can tell the difference between those two people. And it worked fairly simply. It worked based on the principle of reverse complementary binding. So imagine that they have a microchip array with these 700,000 probes on it. Based on the heat map, then you could actually determine this person. Uh, so let's assume that each of these probes have two states. Then the total number of states possible would be 2 to the power of 700,000. Now that number is absurdly large. It's even more than the number of atoms in the universe. So you can be sure that um, the chances of two people having the same heat map would be virtually zero. Here just some of the markers that they use. So they use hair marker, they use teeth marker, tongue marker, all kind of markers. They obviously did not disclose the markers that they use because that is their IP. So I don't know what they use, but they disclosed the number of around 700,000. This is from Illumina. So now that you got all of those markers, you have a heat map. How do you analyze it? How do you find any kind of familiarity with other people? So we would first have to understand a few concepts. One is IBS and IBD. Second is centimorgans. And then the third one would be a third cousin twice removed, or the complication of a family tree. To be honest with you guys, I'm not a native speaker, so this third problem was for me the most difficult. But we'll get to that. So IBS stands for identical by state, which just means identical sequences. It's nothing more than that. IBD mean identical by descendant. Now for human, these two terms are more or less the same because most of the similarity in our genomes are caused by inheritance, and obviously there are mutation that there's a convergent mutation that can look exactly the same even though we are not related, but those are small cases. Unlike viruses, we don't engage in a lot of horizontal gene transfer. So IBD and IBS, for all purposes, are the same. And generally, the longer IBD mean closer relatives, which makes sense. If you share more genome, then you are more closely related. The second concept is centimorgans. Centimorgan is what they measure the length of the IBD in. Centimorgan is a unit of measurement for the length of a segment in the DNA, but it's not exactly. By exactly, I mean if you were to measure it with base pair, then you know 100 base pair is always 100 base pair. Doesn't matter on which chromosome or on which person that you measure it from. 1 centimorgan is different. It is a segment that has 1% of chromosomal crossover event. So longer segment will have more centimorgans because the longer segment will have a higher chance of having a chromosomal crossover event. This vary a little bit between chromosomes. So as I said, 1 centimorgan on chromosome number 1 might not be the same with 1 centimorgan on chromosome number 15%. And why is that? Why would we want to complicate the issue and not just use base pair? Well, because think about it as effective distance. So say that base pair is kilometers and centimorgan is minutes. I can say that I can go from St. Catherine to say Hamilton in 40 minutes, right? But that 40 minutes is different if I'm going through Toronto. 40 minutes from here to Hamilton would probably be like 50 kilometers, but 40 minutes in Toronto would probably be 20 kilometers. So the point I'm trying to get at is because we are trying to find to deal with gene recombination between relatives, the rate of recombination event happen is more important than the actual length of that segment. That's why we use centimorgan and not base pair. Now, to understand the family tree, there's only one. Sorry, there's only two rules. So, first rule is that if you are cousin, that means you are in the same generation. So, for example, it's you and your siblings like right here, and then your siblings, and then your first cousin, second cousin, and third cousin. So, cousins are the same generation. Now, first cousin means going. Uh, First cousin mean that if you go up one generation, then you have then your ancestor becomes siblings. Right. Second cousin mean that if you go up two generation, one, two, then your ancestors are siblings. So first, second, and third are going up. So you see the same thing over here. Third cousin, you go up one, two, three, and then they are siblings. Remove mean going down. So first cousin once removed, mean that they are one generation away from you. You see, and then see this is still your third cousin, and but they're twice removed because they're two generations away from you. This would be more important if we were actually doing the search, but for the purpose of this paper, just know that the bigger the number, first, third, second, the bigger the number, the further away they are from you, as a general rule of thumb. And here is the chart of um, the centimorgans that share between uh, 60,000 relationships. So they have 60,000 relationships that they know how they are related to each other, and then they crunch and then they run all of the tests that we discussed, and then they find these are the length of the IBD segments between those relationships, and they measure it with centimorgan. So, for example, you, this is the self, and your sibling would share around uh, 2,613 centimorgans of identical by descendant segments, IDB segment. And then you and your, say, your first cousin would have 800 centimorgan share, second cousin like 230, third cousin is 73, and so on and so forth. uh, this is a very important chart because it is used as a reference for later studies. Now, with all that background in mind, let's go to the paper's objective. What does the paper want to do? This paper wants to showcase the strength of identity inference of genomic data using long-range familial searches. That's a lot of words. What it means is that we are trying to identify a particular person uh, with just their genomic data. And we are doing it by long range familial search, which means that we're trying to locate their second, third, fourth cousin, and then from those cousins, we would chase back to the person. So we don't know the person, we just have their genomic data. We find their distant relatives, and then we find them back through the distant relatives. So to do this, they would have three secondary objectives. First, they would like to test the inclusivity of this method. I'll talk about that later. And then we test the power of elimination, and then we try to apply it in a real life scenario. So, methodology and results. First, the test of inclusivity. The premise is that we have DNA of an unknown suspect. So we have the DNA, but we don't know who they are. Question is, how likely is that she or her, sorry, he or her have a relative in the current database? So how do we do that? The method is that we assemble the data sets of 1.28 million individuals who have used a DTC provider. We retain individual with at least two IDB segment of 6 centimorgan or more. Less than this, it means that they're too far away. So like the relatives, probably like fourth cousin or something, or sorry, fifth cousin or something, and that would not be very useful. And then we eliminate pairs with more than 700 centimorgan because they would be direct family. And that would not be very useful either. And then we would count the individual that share 30 centimorgans to 600 centimorgan. Or in other words, we're trying to find people that belong in the fourth cousin to the second cousin range of the suspect. And here is the result. Nearly 60% of search, any search in that database, will result in a relative of 100 centimorgan or more, which would be the third cousin. And 15% of them would have 300 centimorgan or more of IDB or IBD. which would be second cousin or closer. If you are familiar with the Golden State Killer, they only needed to find a third cousin to identify him. So 60% of the database the people in the database already have a third cousin, so very significant. And this number would only get better as the database grows with respect to population, as sequencing and biotechnology in general get more and more cheaper and affordable. The database is expected to grow with respect to population. And here is a computer model. They trying to estimate how likely it is that we can find a third cousin in a random database of a random population. So the database size only need to reach around 2% of the population so that we can determine the third cousin of 99% of the population. For the US, that would be, and if we're looking for European descendant, that would be a database of around 2 million. So it's not a lot. It's totally achievable. Now, this is obviously assume random distribution and random sampling of of all the samples, but still, it's a scary number. It's only 2% to guarantee third cousin of 99%. So we have established that the current database is quite inclusive, and it will only get better with time. Now, how so finding the relatives? How big is that of a help? So the premise is that we found a relative of the suspect. Now, how do we find the suspect from this relative? And we would have to apply some filter. So first filter is through the genealogical match that we discussed, trying to find people with 100 to 200 centimorgan of IBD. For serial criminals, the place of crime is almost always within 40 kilometers of the crime scene. Uh, Now this is in the police department, so I don't not quite sure how it happened, but it is the case. So they would apply the filter to include people with only within 160 kilometers. So quite generous the size, and they set the age interval to be plus or minus 5 years, so like a 10-year bracket difference with the matching relatives, and they assume that sex is known from the DNA. Now, from our class, we obviously known that um, the sex is not always known from the DNA. Sometimes it could be deceptive. However, those are minor cases, so we only focus on the majority. So when we apply the genealogical match from a population of about 300 millions, there will be around 855 genealogical match of 100 to 200 centimorgans share. These are the second and third cousin range. Um, and if we limit the search to 160 kilometers from the crime scene, the number get reduced drastically down to 369 people. If we know the sex, that's 50% of them, so around 185. With a 10-year age bracket, there will be 16 or 17 people, which is very manageable. If you a police officer, questioning 16 to 17 people could be done in say 2 weeks. I know this from CSI, and they also consider that this person was a subject to any kind of other research, and we happen to have their birth year recorded, which is permissible by law to be accessible to other researchers. So assume that we also have the birth year of the suspect that has our DNA, then there's only 1 to 2 people left. So that's totally doable. So in summary, uh, Applying this kind of method would reduce the population of the USA of 300 million down to only 16 to 17 suspects. So that is very scary. How does it hold up in a real life scenario? I mean, all of what they did was just hypothetical. Uh, so the premise is that they would find the DNA sequence of an actual human, and then they were trying to re-identify this person. So how hard is it? The method: obtain a genome of a woman, so we know the gender, from the Genome Project, which would be sorry, the 1000 Genome Project, which is publicly available, and we would have some prior knowledge of this person. We know that she lives in Utah with European ancestry, and we know that she was at least alive at the time that the sample was taken. So not a lot, but something. So we would search for a match to GED match, and then we would apply the filter that we discussed on approximate age, location, ancestry, and sex. Here is the result. So the search on the GED match found two males that share 100 and 180 and 171 centimorgan with her, respectively, which means they're in the third cousin and close to the second cousin range. And these two males share between them, so the two male are more uh, more distantly related than they are to the female. So the two males share 62 centimeters between them, which indicate an ancestor of 4 to 6 generations back. Now, this common ancestor was found within just an hour, so that is very impressive. From the ancestor couple that they found in the hour, they were scanned for the descendants to find a person with fitting markers, so like age, location, sex, ancestry, and they found the targeted woman again. Now, this took much longer as the ancestral couples had 10 kids and hundreds of descendants, but they did this in a day. So with a day and a half of work from data acquisition and then to data analysis to final result, probably take them less than 2 days to re-identify a person, which is um, astonishing to say the least. Um, so all that left is some discussion. Now that the authors show clearly how strong and how powerful, dangerous even that these two could be, there are concerns that the same technique could be exploited for harmful purposes, such as re-identification of research subjects from their genetic data. We all know about the um, uh, the witness program from the US. Now, with this kind of technology, the witness program would not be so safe anymore. And the author is very, very concerned that such powerful technique could fall in the wrong hand and advocate for a higher level of data security by treating genomic data as identifiable data. For those of you that don't know, identifiable data require much higher clearance for access and also require stringent procedure to collect, store, distribute, and use. For example, if you were to take part in a scientific research, and they would want to collect some data from you, any kind of identifiable data that they want to collect, such as your name, your SIN number, your phone number, your address, they would have to explain it to you clearly, and then you would have to sign a consent form. If genomic data was treated as identifiable data, then the first step before they can even sequence you would be to ask you to inform you clearly what the purpose of their research and then make you sign a consent form. So a lot safer. And as I said before, name, birthday, scene, address, phone number are all identifiable data. The author's suggestion is that the DTC providers should sign the text cryptographically, so that now if they sign it cryptographically, then the database and analyzer, the third party service, can authenticate their file and request. Um, Now, say that we are a crime organization, right? We sequence somebody, and then we try to send that file to the third party service, to the database, but we don't have the signature of a DTC provider. Then the third party service would just deny that access. So this is a very simple way of protecting it, and if it is adopted, then our data would get a lot safer. So that is all I have to say today. Thank you for listening. I know that sometimes it can be confusing to me at least. So I'm really look forward to discuss this with you guys in the lecture. And if you have any kind of question, feel free to email me, talk to me, anything. All right. Thank you very much, and have a good night.